Hi, everybody. I'm Ishita Jalan, Senior Manager in the Technical Consulting team of Well Labs.
Hi, I am Lakshmikantha. I work as research manager at Technical Consulting along with Ishita. Today, I will be sharing our insights from monitoring, evaluation, and learning for recharge pits, the work we did in Marathwada region of Maharashtra, particularly in Jalna district, focusing on Manta and Partur blocks. The black soils in this region and in Jalna particularly faces a problem of too much and too little water. As you can see in the right picture, so there is a waterlogging, means during the monsoon rainy seasons, the water stagnates on top of the field, leading to the crop loss, means that stagnates for more than 10 days at times when there is a huge pour of rainfall, right? At the same time, though the region receives around 750 to 800 millimeter of annual average rainfall, there won't be enough water in the groundwater or in the wells for protecting their crops for the rabi season. So there is an availability issue post monsoon season. So it's like a paradox where you have plenty of water during the monsoon season, leading to waterlogging, and at the same time there is not enough water post monsoon to support the rabi crops. As a solution to this, locals there have come up with an innovative way of addressing this problem by using recharge pits, which are like a classic intervention implemented here. Basically, trying to address both of the issues. The initial understanding there is the topsoil of Jalna and around area is impermeable, so it's not letting enough water to percolate or infiltrate during the rainy events. So that is leading to waterlogging on the fields. So by introducing a recharge pit, so they are basically puncturing the top impermeable soil and connecting the drainage and the runoff towards the more permeable weathered basalt underneath. So this in a way is capable of solving both the problem of water stagnation that happens on the ground, and also by recharging more water that is generated during the rainy events, it should also help in making the water available for the later months post monsoon for rabi irrigation or rabi protective irrigation. To understand the efficacy of this intervention, we used multiple methods and across multiple scales to understand its efficacy in terms of reducing the water logging and also increasing the water availability by recharging more water. We used multiple methods like infiltration tests, farmer survey, which is a socioeconomic survey, hydrological modeling, and paired watershed analysis, which is a analysis done at the watershed scale. So usually means many of the times the methodologies try to capture the intervention's efficacy at the plot scale, not understanding the watershed scale impact. So we try to cover all the scales as well by doing the experiments at multiple scales and also covering the qualitative informations from the farmers on ground using the farmer survey. So here, just to brief, the hypothesis one focused on like if these pits have to be acting as a conduit uh, to reduce the sorry to increase the permeability, means divert all the discharge and make more water to recharge further. So these recharge pits should be having a significantly higher infiltration rate, maybe 10 to 100x than the surrounding farm infiltration rate. So if the infiltration is happening efficiently, so then the water ponding or water logging should be reduced in these fields. So there should be a reduced crop loss because of this. That was tested in hypothesis 2. And then hypothesis 3 focuses on the recharge component, maybe at the process scale. So we assume at any event, at least 25% of the excess runoff generated during a rainy event within that acre can percolate down via these pits. Just to give you the context, in most of the cases, these pits were implemented at a thumb rule of with a thumb rule of one pit per 1 acre land area. This was done through hydrological modeling and also deploying continuous monitoring sensors on the ground and also inside the pits. The hypothesis 4, as I said earlier, focuses on a watershed scale approach where we use the paired watershed analysis to understand the impact of these interventions, then done at multiple, when done in multiple numbers, the water levels should be improved because of these interventions, leading to more recharge to the groundwater. So since 2021, there is around 60,000 such recharge pits that have been constructed across these two blocks of Jalna. Coming to the hypothesis 1, so the hypothesis states that the recharge pits have a significantly higher infiltration rate, that is 10 to 100x, which we will find out, than the surrounding fields for them to be efficient. So, as I said earlier, we use double ring infiltration tests for understanding the infiltration rates on the field and also on top of the field. The understanding is on farm infiltration rate will be a bit lower, that is leading to the waterlogging, whereas on top of the pit, the infiltration rate should be higher and we will be expecting more steeper slopes here so that it will help the water to percolate quickly and infiltrate quickly. So we did around 22 pairs of such infiltration tests. So 20, that means 22 on-farm infiltration tests. And in the same farm, we did the infiltration tests on top of the pit also to understand the infiltration rate on top of the pit. So this sampling was also done across the three major watersheds, that is Purna, Dudna, and Godavari. And we also tried to cover the elevation profile, means doing this test, some of them in the ridges, some of them in the medium elevation areas, and also some of them in the valleys to cover the topographic differences as well.
So the
Yes, Ishita.
reason we wanted to include different elevations is because our recce visits allowed us to observe that at higher elevations, the thickness of the black soil is lesser as compared to valleys, and
Yes.
automatically that would impact the level of infiltration that would occur from these areas. And to capture that differences and make sure our sample is representative enough, we stratified our sampling across elevation. Thank you.
Yes, thanks, Ishta. So what we found out from this, from the results from this study, there was not much significant difference between the infiltration rates on farm and also on top of the pit. Just to add to what Ishita just said, we also selected pits across which were constructed across multiple years. As I said, the infiltration or the recharge pits were being constructed from 2021 onwards. So we did sample the pits from 2022, means which might have received 2 seasons of runoff. And we also sampled the pits from 2023, which were built in 2023, which might have received only 1 season of runoff. So just to cover the age profile of the pits as well and to understand their impact on the recharge efficacy. So what we found out was, for example, you can see in the 2022 pits, the median infiltration rate here is around 7 centimeter per hour, whereas on that is on the farm, whereas on the pit in the same farms, the median infiltration rate is around 2.5 to 3 centimeter per hour. Whereas when we looked at the median infiltration rates across 2023 pits, that's more or less matching. So there is not much difference between the on-farm infiltration rate and also on top of the pit infiltration rate. So this also led to an understanding that the 2022 pits were also received a lot of silt that have been accumulated on top of these pits, led to clogging up of those pits. So that's what one of the reasons. Even visually, the when we were doing the infiltration test, we could see the silt accumulation, the silt that is being accumulated on top of the pits, and also the experimental results also complemented that finding. So that shows the reduction in infiltration rate on top of the pit. We did also find in some cases where on top of the pit infiltration rates were more than on farm infiltration rate. That would have been the ideal case for the intervention to work well. But at the same time, these pits were not located properly in the landscape. For the pits to be means efficiently functioning, so these pits are supposed to be at the lowest elevation of the plot so that all the runoff that gets generated on the farm gets diverted to that point and then gets recharged there. But these pits which showed higher infiltration rate than the on-farm infiltration rate, there they were placed in such a position, mostly in the higher elevation side, where no runoff entered those pits, also meaning that there was no siltation that got deposited, or there was no silt or clay accumulation that happened on top of the pits. So these were basically pits which were not positioned properly. Few of the things we found while doing our experimentation with the hypothesis one, that siltation of pits was a huge issue. So the existing design of these recharge structures were not meant to capture the silt, and which made it difficult for them to function for more than one or two rain events where the pits used to get clogged up. And at the same time, we also noticed, though these recharge pits were being implemented across the landscape here in these blocks at multiple numbers, some of them were poorly located. That also showed up in few of our data entries, where there was no sign of runoff that has been entered to the pits, and this was also confirmed with the farmers' interaction. And at the same time, there was no mechanism set up for maintenance of these pits. The pits are like means one and done, means whenever they receive runoff, maybe once or twice, so the runoff doesn't come alone. It comes with lot of silt and clay and other soil material. It usually gets clogs the entire top surface, and also for the subsurface of the recharge pit, making it defunct pretty soon. So, for these to function very well, there is a need for frequent maintenance as well. Um, yeah, I will hand it over to Ishita now to explain the hypothesis two and.
Okay. So while hypothesis one was being tested on the ground in the months of March and April in 2024, we were also parallelly conducting the analysis for hypothesis two, which was essentially a farmer based survey where we were trying to test whether water ponding was getting reduced in the fields with the recharge pits. The idea here was to collect testimonials and understand the farmer perceptions to the benefits of these recharge pits. Uh, to be able to sample the right set of farmers for this data collection, we stratified our data across the three watersheds, Purna, Dudhna, Godavari, as well as across years similar to hypothesis 1, 2022, 2023, and 2021. In total, we surveyed about 155 farmers, 119 who adopted recharge pits uh, across the 3 years, and 35 who did not adopt pits, and we call them as control farmers. The approach here was essentially semi-structured questionnaire to gather the details, and a large part of the questionnaire was designed based on our recce visits to the field. In terms of the findings that we gathered, we found out that farmers actually saw a reduction in crop loss to 10%, which was in terms of the control farmers, 63%. So reasonable reduction was seen based on the recall data that was collected from the farmers. And this year, the data is actually represented from year 2022, where it was a normal rainfall year, about 750 which is typically received in that area. So we can understand that the conditions in which agriculture was being done during the monsoon season was normal. And the data was actually collected for two data points. So while here we are talking about crop loss, we also triangulated our data with reduced days in ponding. ponding of the agriculture area. However, those results weren't super reliable because the recall and the confirmation bias tends to, always shift the data points. So in this case, we relied more on crop loss, which was also statistically more significant. And we saw that pits were rather successful as perceived by the farmers. We also try to understand a couple of more things as we dig deeper in through our questionnaire. That while we understood that the recharge pits are actually working based on hypothesis one, what exactly would help in terms of maintaining these pits and to maybe able to function these pits better. And what we realized is that maintenance was a big gap, both in terms of not being widely known that maintenance is needed, and at the same time, how exactly the maintenance would be carried out. So, in one of our data points where we wanted to understand that why maintenance is not being done, a majority of the farmers responded that they did not know maintenance is required. At the same time, when we introduced this idea, we also asked them, that if maintenance has to be carried out, how would you think that would happen exactly for each of those pits? So a large part of the responses came that there could be machine based by JCBs to dig out pits and take away the silt that has been accumulated after the monsoon showers, or otherwise do manual work that farmers were actually ready to volunteer for, to be able to take up all the boulders back from the pit, remove them, desilt it, and put it back. Yeah. Um, Now we are moving on to discussing a little more into detail about the next two hypotheses, which is hypothesis three and four. Um, the methodology or the approach to hypothesis three and four was relatively, more deep dived and also prolonged over a period of time, primarily because we were trying to capture the response on the field of monsoon and post monsoon seasons. So while hypothesis 1 and 2 by nature were tested out in the pre monsoon months of March and April, hypothesis 3 and 4 started to get tested beginning June and ended until the month of January the next year. And therefore, you would see that the observations here actually help us to dig a little more deeper. So, with this, I'd like to hand it over to Lakshmikant.
So, as we spoke earlier, so the hypothesis four mostly focuses on the watershed scale impact of these interventions. Basically, to look at the impact of this intervention on the water table, that in fact leading to impact on water availability for post-monsoon months, that is during December, January for the Rabi crop. The one of the appropriate methods to test this was the paired watershed methodology. So that's what we went with, and we also used a low cost water level sounder that was developed in house, which will give a beep when it touches the water, which made it useful and which made it easier to use for the field associates in the isolated wells to get the readings of the water readings from the wells, right? And then we selected two watersheds. One is treatment watershed with discharge pits, and one is control watershed without any discharge pits. So the sampling involved taking the water levels, that is the from ground level, what is the at what depth the water is at. So this was done both the pre-monsoon, starting from the early June, and also till January of 2025. So covering the entire season of the monsoon, which usually starts from mid-June. So we had pre-monsoon readings and also monsoon readings at the interval of at a monthly interval, and then we also had the readings post-monsoon, that is like December and January, to look at the recession, how the water level goes down. One of the important aspects of this paired watershed studies is to make sure that the pair of watersheds you are selecting are similar. By similar, I mean they should be more or less in the same order of streams and also within the same slope profile. And The size and shape also should be more or less same. In this case, it is around 25 square kilometer for both of them. And if there are any other pre-watershed interventions like a reservoir and those things, those should be more or less in the same ballpark. And then we also checked for the vegetation differences between these two watersheds. So using the average annual NDY for multiple years, I have noted down 2023 here, and we also checked for 21, 22, and 23 to see they are more or less cropped in a similar way. So totally uh, means this is around 50 square kilometer entire study area. We also picked up at least one well per square kilometer for monitoring the water table in that well throughout this season. So because of the edges and all, totally we monitor around 70 wells, 34 from the control watershed and also 36 well from the treatment watershed. So the only difference that should be between these two watersheds is the number of recharge pits. The treatment watershed, as you can see in this figure, had around 463 recharge pits, whereas the control didn't had any. So any change in the water table or any signature change in terms of water availability can be therefore attributed to the presence of these recharge pits here. So what we found based on this 7 to 8 month long exercise, so the numbers you are seeing here are the well depths, usually shallow wells here across the region, which are around with 40 to 50 feet as the average depth. And we can means as we see from June to September, that's the means mid June the monsoon starts, July, August, and those are the important months for getting the southwest monsoon. So the water level in the wells starts rising. So more darker blue, the each point is seeing each these darker blue dots or each blue dots are the well locations. So the more darker the blue means there was a more rise in water table. Means if imagine at the beginning of June the water level in the well was at 30 at 40 feet from the ground level, and it rose to almost 10 or 5 feet below ground level. So that's almost a 30 to 35 feet rise. So that means there is a lot of water that has rised in the well and lot of groundwater which might have happened in the surrounding area, and the water level rose. So that shows the darker blue dots. And similarly, post September or in the early October, the water level starts receding in the wells because the rainfall will become less and the southwest monsoon starts slowly receding. So means as you see, if the drop in water level is more than 20 feet, so that has been shown in the darker red dots. So what we could see is there was no spatial correlation between the rise and fall of the water level, and also there was no visual difference between the uh, rise and fall of the water level and also availability of water between the control and treatment watersheds. So the increase in water level happened between June to September, and the water levels almost reached the peak, and then it slowly started going down by early September, means late September, and then October onwards. So similarly, there was no significant difference in groundwater levels between control and treatment watersheds throughout the monitoring period. It's the previous one, it's the same data, but the previous plot, the map showed the spatial distribution of how the water level is uh, rising and receding. But this is the similar graph. Using the same data, this graph shows in a cumulative way with the box plots how the water level is changing between the control and treatment plots. Just to explain, means the water level, the median water level in the June 6th was around 22.9 feet. And then by September 13th, the water level rose to almost towards the ground level. That's only 3.6 feet below the ground level. So the water level during early June, that is pre-monsoon, was around 22.9 feet below ground level, and it almost rose to 3.6 feet below ground level. It's almost like towards the brim means one can touch the water, groundwater. So it rose to brim by mid-September. There were huge rainfall events during September, early September. September 2nd was one of the uh, high rainfall event day that happened in the landscape. Within a day, there was around 100 or 120 millimeter of rainfall happened. And the coloration of these box plots is complementing the rainfall that happened between the previous measurement and this measurement. So that means this also shows that there is a huge rainfall that happened almost more than 200 millimeter or something that happened between August 6th and September 13th that also led to the increase in the water table here. So the main takeaway here is the rising of the water level, and it's almost reaching the brim in both control and treatment. Even the treatment watershed, the early June reading is around 20 feet below ground level. It almost come to 4 feet below ground level, and then it receded to around 19.2 or around 20 feet below ground level, like it was prior to June, right? Means in the early days of June. So the water level rose came to brim during September and it started receding. So water level rose came to brim in even treatment watershed and started receding. There was no significant difference between the signatures we saw in terms of the water level fluctuation between the control and treatment plots. One important understanding that came out of this study was like the difference in the water level fluctuation between the wells in ridge, wells towards the ridge, and also well towards the valley. Whereas wells in the ridge, both in control and treatment watersheds, here the control watershed well data points are shown in blue, and treatment well data points are shown in maroon. And whereas the comparison we are making is between the ridge and valley across both control and treatment watersheds. So, in irrespective of whether it's a control or treatment watershed, the ridge wells tend to rise quickly. Means there is a lesser water, lesser storage available. Also means that is hinting towards that. So they are rising quickly and also they are falling quickly. It's also because of the topographical factors, right? Means usually the ridge areas are towards the higher elevation, and then there is a slope. Gradient that is taking towards the valley. So the uh, water is going out of the ridge areas pretty quickly towards the valley. That is what these signatures are referring to. So basically, the ridge you can see sharp rise and sharp decline, whereas in the valley there is a bit more flatter rise compared to the ridge and also a flatter decline towards the compared to the ridge. So the ridge and valley means where the well is also plays an important role in terms of the water availability. So yeah, that's one of the interesting thing. I think this gets complemented with some of the understandings that we got from the plot scale. That is the hypothesis 3, where we try to understand the processes that are happening at the plot scale at very frequent data, means high frequency data monitoring. I will hand it over to Ishita now.
In the hypothesis 3 that we want to discuss after hypothesis 4 is essentially at a plot scale analysis that we did from collecting empirical data, high frequency data on the ground by deploying sensors. The reason we wanted to do a plot scale after watershed scale is to give a perspective of a more macro level trends, and then double down on a more micro scale observations that will complement the findings from watershed scale. In terms of the methodology and the instrumentation setup, we deployed a rain gauge for each of the sites that we selected. Here we worked with two sites, two watersheds, one in the village of Neer and the other in the village of Seveli. Both receive slightly different rainfalls. Neer received about 750 mm during the time of our analysis, and Seveli received 580 mm, also a little more higher in the watershed in terms of the elevation as compared to Neer. What we did is that we deployed a rain gauge in each of these watersheds to capture the local rainfall, because the trends in the rainfall is such that they have become highly localized, and we wanted to capture those trends very closely. So this was an automatic rain gauge that was capturing data at an event of the rain. So which means anytime the rain occurs, basically it's getting recorded. And the instrumentation, the observations were essentially recorded from a pressure transducer. In this case, we deployed hobo sensors that are basically capturing data in every 5 minutes from the field. And what they're measuring is the water level, and that water level is coming in the form of the pressure that is being captured by those sensors. In terms of how we deployed these sensors for each site, we had three installations. One was on the top of the pit, which you can see here. It's tied to the pipe, the observation pipe at the center of the pit. There's other sensor that was deployed at the bottom, so which was at the bottom of the 6 feet to understand the water levels fluctuation, and the third in a control plot, a plot which is a simple farm that has not received any pit, and just to understand that how ponding is looking like without any intervention. Um, we had three kinds of pits, two kinds of pits that we utilized. So in the village of Nair, we deployed sensors in two sites: a conventional pit, which was a normal recharge pit without any modifications, and the next was a design pit where we did our own modifications to understand that how we can actually prevent silt from getting accumulated either on the top or at the bottom. So what we did is we raised bunds across around the periphery of these pits at about zero point 0.6 feet. And at the center, we placed mulch so that it can act as a mesh or a network to capture the silt that is coming inside. This was only done here and nowhere else, just to understand that is a response of a design pit different from a conventional pit. And in Savili, we had just one kind of pit, which is conventional pit. Observations were starting to capture beginning July 2024 until November. After November, we did not see any water levels as such in the field, and so the sensors were taken off. So, what you're looking at is the time series that was generated from the village Nair and from the conventional pit, so to say. And what I would like to bring your attention to is, first of all, the high quality data that was captured during this exercise. A lot of the times it is possible that the sensors get damaged, they get stolen, or perhaps the technology did not function as we would have expected. So then there is data loss. I think we were lucky, and fortunately we got a continuous time series from the data we deployed, from the sensors we deployed. And I mean, in terms of both time series representation as well as understanding the various changes, the data was super sensitive. So while you're looking at this graph, I would like to bring your attention to different elements. So in the green, what you're looking at the back is the cumulative rainfall that was captured by the automatic rain gauge at an event interval. In the blue, what you're looking at is the water levels at the bottom of the pit, captured by the pressure transducer. In brown, what you're looking at is the water levels captured at the top of the pit. And here, essentially, what we have done is we have also marked ground level that was there at the side. So any water above this is basically the water that has risen in the pipes that you can see here. So these were the pipes in which the sensors were put and installed in the sites. To understand how the site selection happened, we had to choose villages that were showcasing different rates of infiltration at the surface, as well as to be able to also capture, to be able to select sites that have consecutive fields that can be used both as control plots as well as plots that have pits in them. We also wanted ownership from farmers, so all of these factors culminated into these sites. This is the exact representation of the Nair village, where this is where the design pit was, which is rather upstream. And then here is the control plot, which did not have any pits. And this was the area that was catering to the surface runoff being collected from this pit. And finally, the conventional or the normal pit that was catering to this much area. So we wanted to make sure that even the area that is being catered to is not very different, and the water typically flows from from top to bottom in this direction, and there is a drainage channel here that is allowing the surface runoff, the rainfall runoff, to move out from the entire area. And here we can see there is a dug well, the open well that usually a farmer sources water for. Um, in terms of what trends we expected and what we saw, there were primarily two kinds of events that we witnessed. One is what we have marked here, which is a quick rise and fall twice towards the mid of August, where water levels basically shot up and they quickly percolated inside the pit and they again shot up. So both of these events correspond to two rainfall events. And then there is the second event, which was witnessed, and there was rather some level of water stagnation that was witnessed on the pits, inside the pits. So while event one was something that we had imagined, that was our mental model, that any pit that has to work to be able to infiltrate water to remove excessive ponding as well as recharge aquifers. Essentially, the water should get accumulated on the top and it should quickly percolate inside the ground. However, as the time proceeded and more rainfall was received in this region, we rather started seeing some stagnation. And we sort of wanted to understand why. Um, so we're going to dig deep more into these details and also understand that how these observations are helping us understand the hydrogeology and demystify how these aquifers are actually responding to us. Um, some observations again from the control site and the pit top to understand that were there any differences in terms of ponding and in terms of how the water is behaving, on the top of the pit versus a farm. So what we saw was that the intensity and duration of water logging was not very different. What you're looking at here is that in the brown, these are the water level observations in the pressure transducer captured for the control site. And in the blue, what you're seeing is the pressure transducer water levels for the top of the pit. And you can see that they rather overlap. So there wasn't a lot of difference in how water accumulation was happening at both sides. Typically, at the start of the rainfall event, there was a quick rise and fall again because the groundwater levels weren't maybe that high. I'll talk about it more in the subsequent slides. And then in the subsequent rainfall events towards the end of August, towards end of September, we see that there is a prolonged waterlogging for almost 14 days to 4 days. So these are some observations that we'd like to keep in mind. So to maybe step back from all the discussions around specifically, observations and the trends, what we wanted to also understand is that what are the conceptual processes that actually govern the functioning of a recharge pit. So what you're looking at is the representation of the field. Typically, in this case, we wanted to replicate what is the cross section of the field from near. So there is a conventional pit that is placed, and on the side there is also a design pit. Adjacent to that is an open well, and open well in this case an indicator of the water level in the aquifers. So, like how we have deployed pressure transducers on the field, the red dots tell you that one of it was placed at the bottom of the pits, both in conventional and design, and the other two were placed at the top of the pit. Now, this is a schematic diagram, and I would like to point out here the different elements that will help us understand how do we make a recharge pit work. So, as I said, criteria one, there should be enough available subsurface storage. So this thickness that you're looking at in gray should be adequate to be able to capture all the runoff that is coming into these pits and percolating down. The second criteria is that the surface runoff to the pit should reach as an infiltration excess runoff. Now, this means that while we are saying that perhaps black soil is acting as an impermeable layer, therefore, whenever water comes in, it's unable to infiltrate the water through it, and therefore, any runoff or any excess water that is on the fields is actually because soil is unable to intake it further. So now that water should actually reach these pits. That is the second criteria for these recharge pits to be making sense on the field. And the third criteria is that the volumetric rate of water conveyed from surface to aquifers through these pits should be much more than, say, the rate of infiltrated water through ponded area. So it's a slightly different criteria to understand that the whole sense around the quantum of water getting inside the ground should be more than what how much water is actually accumulated, say, as ponded and get infiltrates into the ground. So these are the three criterias that we'd like to evaluate and assess in the next three slides to understand that how do our observations tell us the story? Do they validate these criterias, or they tell us that perhaps these criterias are not occurring on the ground and therefore we might see a different outcome? So looking at criteria one, what we learned from the field and from the observations is that aquifers in the valley area specifically are quickly getting recharged and they're becoming fully saturated. So while at this point of time, going back to the trend analysis for pressure transducer water level time series, at initial events, which was a quick rise and a quick fall, we actually saw the phenomena that is represented in this figure, which is that water is entering from the pits, it's filling up the pit and quickly percolating inside the ground. Now, what is different that is occurring in time two? Time two is where we're actually seeing a lot of stagnation, which is that at the bottom of the pit, sensors are telling us that there is a very high water level inside the pits. And that's because these aquifers have actually saturated to the brim and the water has nowhere to go, and it's pretty much reflecting a very stagnant trend in the data that we're looking at. And the reason this is happening is because these are massive basalts, and massive basalts are characterized by very small storage. These are essentially like layered aquifers. So if you're in a layer that is shallow, it tends to get filled up very quickly. So this T2 is actually the same event that Lakshmikant, my colleague, was referring to, which received about 100 plus rainfall in a single day. And as soon as that happened, the aquifers didn't have any more space. So what you're looking at here, which is T1, is essentially an infiltration excess waterlogging on the top of the surface. And in T2, what you're looking at is actually saturation excess waterlogging. Um, yes. And you're actually looking at, in this case, in the blue, the conventional pits curves. And then in the browns, you're looking at how water levels are responding for the design pit. So the reason that there are no water levels in time one in the design pit is because of the reason that there is a bunding around the pits. It's preventing smaller runoff events to enter, and therefore there is no water per se that is being reflected inside the pits. Now, the second criteria, that the runoff that is being generated in the field should be infiltration excess runoff. The question is that really happening? Because we saw that the infiltration rates here are rather high. Based on our hypothesis one, we found out that the median rate of infiltration based on 22 samples was 8.8 centimeters per hour. Now, this is a good enough rate of infiltration. And then we can actually corroborate this data set with a larger sample that was taken by CGWB for a regional level observation in Marathwada, where they captured observations from Jalna district, Aurangabad district, and Latur district into about 23 samples. And the median rate of infiltration even here is about 2 centimeters per hour. Again, high enough to not let infiltration excess runoff generate into the area of study that we're looking at. So it doesn't qualify for the criteria too. And on the other hand, if you also try to understand the other trends or the regional level perspective about water logging, we'll see that there are patches. This is a graph that you're looking at again from CGWB, where they're showing us the post monsoon depth to water level data for November in 2017 for Jalna district. What we're looking at is that the green patches tell us that the water levels are shallow, about 2 to 5 meter below ground level, and the yellows and the pinks, which are relatively rare, but they are there. They are about 5 to 20 meters below ground level. Now, these are the patches that have actually deeper aquifers, and these are the areas that are also not, receiving saturation excess water logging. So then, in that case, we have to understand that we have to question ourselves that does it make sense that we can actually deploy these recharge pits in these areas and get rid of the problem of shortage? But the answer actually lies in the fact that when we looked at hypothesis 4, we found out that the water doesn't stay. There is recharge, there is water entering into the aquifers, but because these are perhaps higher elevation areas, the water quickly moves out of the area and therefore it has poor residence time. So that also helps us understand the variance, the variability in the region, and why not, a recharge pit might work. And to also additionally share observations from the ground, and also to understand whether there is reasonable amount of runoff being generated, or there is reasonable amount of runoff that is being infiltrated from the pits versus the soil. What we learned in Savili, which is the second site in which we deployed the pressure transducers, we learned that there was no runoff that was seen altogether at the top of the pits or bottom of the pits. How do we know that? Look at this graph, and what we're showing here in the blue is actually the water level time series from July until October for the bottom of the pit. And then in the brown, you're looking at, in the brown, light brown and the dark brown, you're looking at water levels both at the control side as well as at the top of the pit. And both blue and browns are practically at negative levels, which is telling us that there was no water sensed by these sensors at all. So the soils are actually pretty good in terms of the infiltration rate here. It was about 12 centimeters per hour when we tested it using double ring infiltrometer, and the well water level also showed us that the water here was about 20 meters below ground level. So the aquifers are deep. However, even the soils are very permeable. So therefore, we could not see any runoff being generated here. And to also reiterate the findings from the hypothesis one results for infiltration, both we would see that on farm and surface of the pit, the results weren't very different. So yes, this is about the findings that we had for hypothesis 3, using empirical observations from the field
Yes.
by deploying high
Yeah.
frequency sensors.
Slight correction. I think it's a 20 feet below ground level.
Okay,
Yeah.
yeah,
Yeah.
yeah, yeah.
No problem.
Thanks for that.
So even then, it's much below the bottom of the pit. Means usually the pit bottoms at 6 feet from the ground level, but whereas the water table in the downstream well, the well is not even, if you look at the elevation profile, it's not even 10 or 20 meters away from the pit in terms of the elevation slope. So the water
Yeah.
table is almost at 20 feet below ground level. That means there is enough strata between the bottom of the pit and the water table for the water to go in. Yeah.
Okay. Um, a couple of observations that we wanted to take from the field to also understand that while the two sites, Nair and Sabli, are telling us a story, what is the pattern across the entire district? And we actually captured water levels from the shallow wells that are the primary source of water for irrigation. You could see here, and all of these images, right from these different locations in the district, that all of them were filled to the brim. So the regional water levels altogether were very high during the monsoon period, and these were captured in the month of September. That was pretty much towards the end of the monsoon. There were also a few perennial, a few seasonal channels that were there that had water gushing out like anything. So it clearly tells us that the base flow at that point of time was also very high, which was coming out in the form of streams and creeks from these seasonal channels of water. Um, and it tells us that overall the water levels in that area were very high, and practically any additional recharge had nowhere to go. All right, over to you, Lakshmikant.
Thanks, Ishita. So the findings basically means, just to summarize all the hypotheses together. Um, the first hypothesis, the hypothesis was that on top of the pit, infiltration rates will be around 10 to 100 times more than the on top of the farm. So infiltration rates. But based on the double ring infiltration tests done both on top of the pit and on farm infiltration tests, we didn't see much difference between the on farm infiltration rates and also on top of the pit infiltration rates. There were few outliers, but most of the times those outliers were uh, placed in a wrong position where there was no runoff that was entering those pits. Coming to the hypothesis two, I think Ishita did cover it, and then we we also came across farmers telling that there was an reduction in the crop losses. But at the same time, when we did this study, the rainfalls in 2023 was a bit less compared to what happened in 2022. So the farmers' perceptions, based on what farmers told, they did say that they did see some reduction in crop losses in the treatment plots. So then hypothesis three. So we were expecting its most granular study, means we were trying to understand the processes that is happening at the pit level. So some of the interesting observations that came there are like, so one is, as Ishita said, even if we take the average infiltration rate at the Marathwada level, which is around 2 centimeter per hour, so that means if there is 1 feet of even if there is a 40 centimeter, I mean, almost 1.5 feet of water is there, so that should get reduced within a day, within 24 hours. There is a capacity of 48 centimeter per day infiltration rate, even if we take 2 centimeter per hour infiltration rate. So it's very unlikely when there is a water lagging event happening in these places that can be attributed to the infiltration excess water logging, because the infiltration rate was good both from our experimental studies and also from the study and measurements done by CGWB. And coming to the last hypothesis, in which we were trying to look at the watershed level understanding of what is happening, means whether there is a dent that is being made at the water availability by changing the groundwater levels because of these interventions, that we couldn't agree with the hypothesis, because we didn't see any trends or the signature differences between the control and treatment watersheds. Both are more or less same, but the study helped us understand the regional dynamics or the watershed level dynamics of the groundwater movement. Means we could see the ridge wells were, means, running out dry quickly compared to the valley ones. So the water towards the ridge, because of the topography, is oozing out or getting away from those areas pretty quickly and contributing to the valley wells. Yeah, we are coming to the final slide of this presentation. I think initially we started with the black soil. Region of Jalna in Marathwada faces a problem of too much and too little water. That's true. And what we learned towards the end of the study, I think I would like to hand it over to Ishita to summarize the slide. And
Okay,
yeah, I will jump in towards the end.
absolutely. Let's do that. So I think we wanted to use a schematic diagram to explain that how aquifers are actually placed in that region, because basaltic aquifers are very unique, and as a result of that, they pose a very unique hydrogeological characteristic that affects storage, affects how long does the water stay. And this is a very representative way of looking at the entire intervention and the represent and the intervened area. What you're looking at is that these are, in the gray, these are weathered rocks that are essentially the ones that are storing water in it, followed by a massive basalt layer, which is highly compact in nature and does not have any porosities or secondary storage to allow water to store. And they're alternating with each other because each of them, as a pair, actually represents a single lava flow. Now, as these are series of lava flows that you're looking at, so in this case, you're looking at three of them, and they have entered the planet Earth at different points of time as they erupted from a volcano. Each of these gray layers have undergone a certain level of weathering, and as a result of which they gained porosity and they started storing water. Now, in a conventional case, you would have imagined all of this depth to be the storage. But because these are massive basalt layers that are intervening, they create this limiting layer because of which the storage becomes only as much as the thickness of the gray layer that we're looking at. So typically, while a well might be able to dig into the entire strata until encountering massive basalt, which is about 25 to 30 feet deep into the ground. The recharge pits that we're looking at is how they are placed here in the field. So they are about 6 feet deep, basically overcoming only the topsoil layer. uh, yeah, so I think this helps us visualize and understand that how perhaps the storage is impacted. So when we say that aquifers lack storage or they're limited in storage, we essentially mean that we have only this much to fill up, and as a result of which, when rainfall comes in, the water level in these aquifers rise up quickly to reflect in the wells that they have filled up to the brim.
The symptoms that we started with were true. Means there is substantial waterlogging and there is a lack of post monsoon water availability when wells go dry. And but the processes that are leading to those things were not attributed properly. So initially, the assumption was, or the understanding in the landscape was, the impermeable black cotton soil on the top, right? That is the problem or the villain of the story. That's not letting enough water to percolate. That's leading to waterlogging. That's leading to waterlogging, and it's also not letting the water to recharge the water table. So that is leading to the problem of waterlogging during the rainy season, leading to the crop loss. Since that logged water, which would have been infiltrated and further recharged the uh, uh, aquifer, that's not happening because of this. So that's why we are not getting enough water post monsoon. That's There is a water availability problem. So by puncturing this impermeable black soil, we will be able to solve both the problem of uh, waterlogging and also the problem of the recharge, which will make the water available for the longer time. But the thing was that the waterlogging that was happening was not happening because of the uh, impermeable nature of the black soil, at least for the areas we studied. It was happening because the aquifer, which had very low storage, mostly in the vesicular layers and or the weathered rock layers, very low storage that used to get filled up pretty quickly, like in the conceptual diagram Ishita showed and explained, pretty quickly, and leads to waterlogging and at the same time. And even if it is in a valley area, so the long prolonged waterlogging is the case. Means sometimes it goes for months also. In With some of the farmers we spoke who are sitting towards the valley, the water won't leave the field for many years, for many months at least. So that was because of the saturation of the entire aquifer, and also that water oozing out towards the valley areas. Whereas coming to the water availability issue, that was mostly prominent towards the means, because we could see few of the means wells or the open wells towards the valleys, they tend to dry up in means they tend to hold water for longer time. Means they used to dry up in April, May, or sometimes they used to have at least 3-4 feet of water at the bottom till the next monsoon arrives. So whereas towards the ridges, the water, because of the topography and elevation difference and the slope, the water oozes out or the leaves the ridge area pretty quickly, and water moves towards the valley. So the water availability problem was because of two reasons. One is the lack of storage, and also because of the topography. Those were the two reasons. But whereas the other problem, the water logging problem, was because of the lack of storage and quick saturation of the aquifer, rather than the lack of infiltration capacity of these black soils, right? So just to conclude, so that was the problem. That's the main takeaway from this exercise for us. That was like an how important it is to diagnose the problem at the first case before uh, going ahead with any interventions. With a proper problem diagnosis, the intervention recommendation could have been completely different, right? Means rather than investing in recharge pits, we would have thought of some systemic solution packages, like having landscape approach, or which includes proper drainage, so that the even though if it is saturated waterlogging, you can drain the plots with using the elevation gradient. You can using a proper drainage network, you can drain it and have a community pond or something like that. And also something like a raised bed farming that could help in reducing the root rotting that happens because of the waterlogging towards the valleys, right? And at the same time, so since it's the water availability problem, especially for the people towards the bridges, some storage structures like community farm ponds or something that could have helped them retain the water for longer time. Means the residence time, as Ishita rightly mentioned, is a big problem there. So increase the water availability for the longer duration. So some community storage structures towards the ridges, like community farm ponds, could have helped address the problem of rabi season protective irrigation and so on. Thanks a lot. Means it was a very fruitful means learning exercise for us, and we enjoyed the field work we did there, and we appreciate the support of our field associate Avinash, who helped us in data collection, and also Dhananjay, who helped us in the data collection for the paired watershed exercises.
Yes, I think it was a great experience, and my gratitude to Environmental Defense Fund, who were our official donors for this project. They have been very generous and extremely enthusiastic about their participation in the project. I think I would like to also briefly introduce and mention the monitoring and evaluation focus that we have at Well Labs. As a technical consulting and a group of interdisciplinary professionals that we are in the team, we are constantly striving to influence monitoring, evaluation, and learning in the water sector to make steps towards a robust evaluation, impact evaluation, to understand how water interventions, how investments in the watershed sector are actually moving the needle on the ground. And when I say moving needle on the ground, I actually allude to water security, livelihood enhancement, biodiversity, ecological flows in the rivers and streams. And essentially, because so much money is flowing into the sector, into the grassroots level interventions, initiatives, there is a need for us to understand that which are the gold standards that we are trying to work with, and which are the scalable solutions that we can adopt at a much wider scale. And for that to happen, I think impact evaluations make a lot of contributions to the conversation for us to understand what works where, how good it is, and also reasonably qualify certain solutions from mediocre ones, to be able to do justice to both the investments as well as the efforts. Yes. Thank you.